Greetings of the day to all of you. Today I am going to discuss about analysis and design of PWM techniques from line current ripple perspective. I will write here analysis and design of pulse width modulation techniques, that's PWM techniques, from line current ripple perspective. We will try to learn in this lecture, we will try to study in this lecture about various types of PWM techniques from the perspective of current ripple or stator flux ripple. And we will apply different switching sequences which are used in different types of PWM techniques. And we will see that how does this current ripple vary with switching sequence, and what are the switching sequences which result in less current ripple, and what are the switching sequences which result in more or higher current ripple. Okay, so in order to discuss those PWM techniques from line current or stator flux ripple perspective, let us revisit what we have studied in our last couple of lectures. Just a recap of that. Okay, if you remember, we were discussing the ripple, stator flux ripple, and we have seen that the stator flux ripple is something like this. For example, this is your Q axis, this is D axis. Let us take the switching sequence 0, 1, 2, 7. So null vector 0 is first applied. Okay, then active vector 1 is applied, active vector 1 is applied, then active vector 2 is applied. For example, this is active vector 2, and then null vector 7 is applied. So this is the stator flux ripple. Okay, so this is psi tilde. Psi tilde means stator flux ripple. When the switching sequence is 0, 1, 2, 7, the stator flux ripple vector moves like this along this triangular trajectory. This is the trajectory. Okay, and if you resolve this into D component, if you resolve this stator flux ripple psi tilde into D component psi D tilde and Q axis component psi Q tilde, it looks like this. We already know something like this. This is time axis and this is our psi D tilde axis. Okay, we know that when null vector 0 is applied, it grows in this direction and it has no component along D axis, so it is 0. So that means when null vector 0 is applied for time interval tz by 2, its D axis component is 0. I mean the stator flux D axis, stator flux ripple D axis component is 0. Then active vector 1 is applied. When active vector 1 is applied, the stator flux ripple, it becomes less negative and then it becomes positive. Okay, now since we are discussing the D component, psi D tilde, okay, when active vector 1 is applied, you can see along D axis it increases like this. So it increases along D axis. So when active vector 1 is applied, and it is there for time interval T1, and then we apply active vector 2. When active vector 2 is applied, this D component, it falls and it becomes 0. Psi D tilde becomes 0 when active vector 2 is applied for time interval T2. And then null vector 7 is again applied. It is along Q axis. It has no component, the stator flux ripple has no component along D axis when null vector 7 is applied. So it is 0 once again when null vector 7 is applied for time interval tz by 2. And we already know that this line is D. Okay, so and we already know this D is equal to VDC sine theta s into T1. Let us write sine alpha. Okay. In our last lecture, we used the notation theta s. That is the angle subtended by rotating reference vector. We can represent or we can denote it by alpha also. So therefore D is equal to VDC sine alpha into T1. So this is D. Okay. So this is about psi D tilde. What about psi Q tilde? We have already done it. We have done this exercise in the last class. Psi Q tilde is like this. You can see when null vector 0 is applied, the Q axis component of stator flux ripple grows in this direction. It becomes more and more negative. Okay, so it becomes more and more negative, and it's maximum negative here. And what is its value here? Its value, if you remember, is 0.5 QZ. Right? QZ is zero error voltage vector, volt second. We have already defined these terms QZ, Q1, Q2 in last lecture. And then active vector 1 is applied. When active vector 1 is applied, your stator flux ripple, which was maximum negative here, it becomes less and less negative, and then it becomes positive also when active vector 1 is applied. So it is something like this. This null vector 0, this active vector 1. Okay, and it increases from 0.5 QZ to 0.5 QZ plus Q1. Okay, the value here is 0.5 QZ plus Q1. Here the value is 0.5 QZ. Here when active vector 1 is applied, it increases, it becomes less negative than 0 and then positive. And here its value is 0.5 QZ plus Q1. This is when active vector 1 is applied. What will happen when active vector 2 is applied? When active vector 2 is applied, it increases. Its Q component increases, but by a small amount, like this. It increases slightly. Okay, and it increases from 0.5 QZ plus Q1 to 0.5 QZ plus Q1 plus Q2, which is also equal to minus 0.5 QZ. We have already noted it in the last lecture. And then this is when active vector 2 is applied. Then null vector 7 is applied. When null vector 7 is applied, the Q axis component of stator flux ripple, it moves in this direction and it becomes 0. It goes back to origin. That means it drops to 0. 0 ho jata hai. Right? And we have already, I have already given you one equation for finding, for example, you have to now find the RMS value of D axis component of stator flux ripple and RMS value of Q axis component of stator flux ripple. What is the method for that? I have already told you root mean square value means you have to first square these lines. This line you square, it becomes a parabola. Square this line, it also becomes a parabola. Then in order to find the mean square, find the area under these two parabolas. Okay. Similarly, as far as this Q axis component of stator flux ripple is concerned, you in the first subinterval, you square this line. When you square this line, it becomes a parabola like this. Then you square this line, it is another parabola like this. Then you square this line, it's another parabola like this. Then you square this line, it is a parabola like this. So you find area under all these parabolas. Okay, how to find area under these parabolas? For that purpose, I have already discussed with you, and we have derived a generalized equation, and that is area is equal to y2 minus y1 by 3m into y2 square plus y1 square plus, y2 square plus, and this is y2 y1, y2 square plus y2 y1 plus y1 square. Okay, y2 by m is x2, m is the slope, y2 by m is x2, and y1 by m is also y1 by m is x1. So therefore we can write area under parabola. This equation is for area under parabola. So you can apply for all these parabolas and you can find area under these parabolas. That will give mean square. Okay. So area is equal to, so y2 by m is x2 minus y1 by m is x1. x2 minus x1 by 3 into, I can first write y1 square plus y1 y2 plus y2 square. This formula we have already, generalized formula, we have derived in the last class. And then we applied this formula for finding the areas of these parabolas. And if you remember, we found the area of these parabolas. For example, we found area under this parabola. And what was that area equal to? If you remember, the area under this parabola was, that was d square, for example, area under this parabola. Let us call that the area under this parabola, if I divide that by ts, where ts is the subinterval time, subinterval duration, ts, that will give mean square value. Okay, this is the square value, this is the square. Find the area under these parabola, that will give, and divide that by ts. Ts is the subinterval duration, that will give mean square. Okay, so mean square of dx component of stator flux ripple, let us call that fd. Let us call that fd sub square. fd means f for flux, d for d-axis. It is the stator flux ripple along d-axis in a subinterval. So fd square, and that is equal to, what is that equal to? If you apply this formula, that is x2 minus x1 by 3. x2 minus x1 is basically this time. This is t1 plus t2. So this is t1 plus t2 by, then it is 3. I will write by 3 into ts. I divide this t1 plus t2 by ts in order to find the mean value, square mean value. Okay, this is the square, and in order to find the mean, use this formula and divide this by ts also in order to find the mean, multiplied by d square, multiplied by value of this line. What is this line value? Its value is d square, or I can write d component stator flux ripple fd square in a subinterval, or in a subcycle. Sorry, it's not subinterval, it is subcycle ts. It is equal to, it is given by 1 by 3 into d square into t1 plus t2 by ts. Fine. Okay, in a similar way we can find area under these parabolas. If you remember, we found areas under these parabolas in the previous lecture. We divided this whole stator flux ripple along q-axis into 4 subintervals. When null vector 0 is applied, this is our first subinterval. Then active vector 1 is applied, this is the second subinterval. Then active vector 2 is applied, third subinterval. Then null vector 7 is again applied, fourth subinterval. So therefore, area under this parabola in first subinterval, let's call that q1. If you remember that q1 is, use this formula, x2 minus x1 by 3. What is the value? What is the value at the end of, what is the value of this line? The value of this line is 0.5 qz, as you can very clearly see. It is 0.5 qz, right? So it is, before I write 0.5 qz, what is the time interval? यहाँ से यहाँ तक कितना time interval है? This is tz by 2. That is, it is equal to 0.5 tz. So x2 minus x1 is basically tz by 2. That is 0.5 tz divided by 3. And I will divide it by ts also in order to find mean square value. Okay. Then multiplied by y1 square plus y1 y2 plus y2 square. This line has only one value. Here it has 0 value and here it has 0.5 qz value. So y1 is 0 and y2 is 0.5 qz. So therefore it will be y2 square, that is 0.5 qz whole square. We have already found it in last lecture, this equation. This is q1. Then what about area under this parabola in second subinterval, q2? What is the time interval? This time interval is t1, as you can see. t1 is the time interval for which active vector 1 is applied. So it is t1 divided by 3 ts multiplied by y1 square. Now it has two values. This is y1 and this is y2, this line. y1 is 0.5 qz square plus y1 into y2. y1 is again 0.5 qz into y2. What is y2? y2 is 0.5 qz plus q1. 0.5 qz plus q1 plus y2 square, and y2 is 0.5 qz plus q1 whole square. So this is my q2, right? In a similar way, in the third subinterval, I will find area under this parabola when active vector 2 is applied. So area under this parabola is time interval, this active vector 2 is applied for time interval t2. So this is t2 by 3ts into, again, y1 square. It has two values. This is one value, this is another value. This value is 0.5 qz plus q1. So this is 0.5 qz plus q1 square. So y1 square plus y1, y2. y1 is again 0.5 qz plus q1, 0.5 qz plus q1 into y2. What is y2? y2 is 0.5 qz plus q1 plus q2, and we have proved in previous lecture that it is equal to minus 0.5 qz. So it is minus 0.5 qz plus y2 square. y2 is same, that's minus 0.5 qz whole square. So this is q3. Okay. In a similar way, we can find q4, that is area under this last parabola in fourth subinterval. What is time interval for which this is applied? This is applied for a time interval tz by 2, that is equal to 0.5 tz. Okay, so therefore time interval is 0.5 tz by 3ts into, what is the value? This is y1, this is y2. y2 is 0 and y1 is minus 0.5 qz. So it is simply minus 0.5 qz whole square. That's all. So these are the areas under different parabolas. So these areas will basically give us mean square, not root mean square, mean square. Okay, what we have done, we have squared all these lines, those resulted in parabolas, and we have found areas under these parabolas using this equation, and we divided this whole curve into 4 subintervals, and we got 4 areas, q1, q2, q3, q4, and therefore total mean square is q1 plus q2 plus q3 plus q4. That's total mean square. Okay, and as far as this qz is concerned, if you remember qz, let me first define this qz. qz is equal to minus vref into tz. We have defined it in last lecture. Okay, what is q1? q1 was also defined in last lecture, that is vdc cos alpha minus vref into t1 when active vector 1 is applied. The difference between what is applied and what is the desired value, this is what is applied and this is what the desired value. What is applied is vdc cos alpha and what is required is vref. So vdc cos alpha minus vref is the error voltage vector. Multiplied by t1, it gives error voltage, error volt second vector. So that is q1. q2 is volt second error when active vector 2 is applied. And if you remember, when active vector 2 is applied, we have found in last class that then the vector which is actually applied is vdc cos of 60 degrees minus alpha minus what is desired vector. Desired vector is vref, and multiplied by time interval t2 for which active vector 2 is applied. So this is within the brackets, this quantity is error voltage vector, and when I multiply it by t2, it gives error volt second when active vector 2 is applied. Okay, so that is this that is the value of this line here. So qz we know, q1 we know, q2 we know, and then we know t1, t2 also. For example, what is t1, what is t2? We already know. We also know that t1 is equal to vref into sine of 60 degrees minus alpha divided by vdc into sine 60 degrees into ts, where ts is the subcycle, subcycle duration. Dwell time t2 is equal to vref into sine alpha divided by vdc into sine 60 degrees into ts, and tz is equal to Ts, total subcycle interval, minus T1 minus T2. So therefore, we have equation for Qz, we have equation for Q1, we have equation for Q2. And in these three equations, we are using the term reference vector and we are using the term Tz, T1 and T2. This is here T2. T1 is this, T2 is this, and Tz is this. Okay. So therefore, Q1, we have already found, for example, what was Q1? That was 0.5 Tz by 3 Ts into 0.5 Qz whole square. Qz is this. And इसमें Tz term आप use करते हैं, that is Ts minus T1 minus T2, and T1 is this, T2 is this. Substitute here, that will give you, stator flux Q axis ripple in subinterval 1. Similarly, in subinterval 2, we already have developed an equation just few moments back. Subinterval 3, and finally subinterval 4. So therefore, what is the total stator flux ripple along Q axis? Let us write that. So therefore, Q axis ripple in a subcycle, square of that Q axis ripple in a subcycle is equal to Q1 plus Q2 plus Q3 plus Q4. That's it, we know. FD square, D axis, stator flux ripple is given by this equation, and Q axis stator flux ripple is given by this equation. Therefore, what is the total stator flux ripple? Therefore, the resultant stator flux ripple, F square sub in a subcycle, is equal to FD square in a subcycle plus FQ square in a subcycle. And we have equation for FD square, which is this. We have equation for FQ square, which is this. So that will give us stator flux ripple in a subcycle as square root of FD square in a subcycle plus FQ square in a subcycle. Fine. We already have equations for FD square. We already have equations for FQ square as given by these. So this will give us total stator flux ripple. This will give us RMS value of stator flux ripple. What is within the brackets is mean square. And when I take square root of this, root means square value or RMS value of stator flux ripple. Fine. So this is all that we have already discussed in previous class, in last class. This was just a recap of that. Now, as far as equation for dwell time T1 is concerned, we have just now written this equation. T1 is equal to Vref into sine of 60 degrees minus alpha divided by VDC into sine of 60 degrees into Ts, sine of 60 degrees into Ts. And from this equation, we find that this dwell time is a function of three parameters: rotating reference voltage vector Vref, and it is also a function of spatial angle, the angle made by this rotating reference vector at any instant of time, which is called spatial angle, S-P-A-T-I-A-L. That's angle made in space. And it is also a function of subcycle interval or subcycle time, Ts. So therefore, T1 is a function of Vref. It's also a function of alpha, and it's also a function of Ts. In a similar way, the equation for dwell time T2 is Vref into sine alpha by VDC into sine 60 into Ts. So this is also a function of these three parameters, Vref, alpha and Ts. So this is also a function of Vref, alpha and Ts. Very interestingly. And what about Tz? Tz is total subcycle interval minus T1 minus dual time T1 minus dual time T2. And since T1, T2 are a function of Vref, alpha, Ts, so Tz is also a function. The zero vector time or null vector time Tz is also a function of Vref, alpha and TS. Fine. So therefore, what about QZ? Okay, QZ we have just few moments back found. QZ, what was QZ? That was minus 0.5, that was minus Vref into TZ. So Vref is there and TZ is there. Since TZ is a function of Vref, alpha, TS, so QZ is also a function of rotating reference vector, spatial angle and subcycle interval. What about Q1? Q1 is also a function of Vref, alpha and TS. What about Q2? Q2 is also a function of Vref, alpha and TS. So therefore, whatever parameters we are using in those equations while finding FD square subcycle and FQ square subcycle, mean square of D component of stator flux ripple along D axis and mean square of stator flux ripple along Q axis. Since they use all these terms, so therefore FD square is also a function of these three parameters, Vref, alpha, TS, and FQ square is also a function of this. And what is the total RMS value of stator flux ripple over a subcycle? That is under root of, just few moments back we have written that is under root of FD square plus FQ square over a subcycle. Since these are functions of these parameters, so that means RMS value of stator flux ripple F sub is also a function of rotating reference vector, spatial angle and subcycle timing. Okay, so this is very interesting. So if you find, you can find then equation for this F sub in terms of Vref, in terms of alpha and in terms of TS. I'm not going to derive that equation. I'm going to give you the reference of the paper where from you can get derivation of that equation. I'm going to give you the result. The RMS value of stator flux ripple F sub, it is given by this equation. C naught, which is a function of alpha, into Vref square, plus C1, which is also a function of alpha, into Vref cube, plus C2, which is also a function of alpha, into Vref raised power 4 whole raised power 1 by 2 into TS. So this is the mathematical equation for RMS value of stator flux ripple. This is RMS stator flux ripple. Just few moments back we found its equation in terms of QZ, Q1, Q2, D, etc. But you can write this equation as a polynomial. What is this? This is basically a polynomial in this form. Okay, you can derive it. For derivation you can refer to that research publication or research paper whose reference I am going to give hopefully at the end of this lecture. So therefore RMS value of stator flux ripple you can write as a coefficient C naught, which is a function of alpha, into Vref square plus C1, which is also a function of alpha, Vref cube, plus C2, which is also a function of alpha, Vref raised power 4 whole raised power 1 by 2. That is root mean, square root of this, because this is RMS value, multiplied by TS. So as far as C0, C1 and C2 are concerned, they are trigonometric functions of alpha. Trigonometric functions of alpha. So this is a function of alpha, this is also a function of alpha, this is also a function of alpha, and are different for different switching sequences. For different switching sequences. Now I am coming to that now slowly. We are going to see the effect or influence of switching sequences on stator flux ripple. I have made a statement here that C0, C1, C2, these coefficients are functions of alpha, and simultaneously I have also written that the C0 value of C1 and value of C2, they are different for different switching sequences. Okay, for different PWM techniques, because different PWM techniques use different switching sequences. So their value is different for different switching sequences. Before I come to that, from this equation you can also find that the RMS value of stator flux ripple is directly proportional to this TS. So F sub is directly proportional to subcycle time TS. Okay, so what does it mean? It's very important. It tells us that if switching frequency is halved, so this means, or this the meaning of this is that if switching frequency is halved, मतलब अगर आप switching frequency half करेंगे, because what is switching frequency? Switching frequency is 1/2 TS. Okay, we have two sub-cycles. So for example, if you take switching sequence 0, 1, 2, 7, then you have in the reverse order 2, 7, 2, 1, 0. This is one sub-cycle, this is another sub-cycle. Total is 2 TS. So 1/2 TS is your switching frequency. So if switching frequency, so since Fs is equal to 1/2 TS, or we can say Fs is proportional to TS, if you are, or in other words, TS is inversely proportional to switching frequency. If you are halving the switching frequency, you are making it half, what will happen to TS? TS doubles. If switching frequency is halved, TS gets doubled. And when TS doubles, TS value, time interval, that means sub-cycle time interval doubles. That means RMS value of stator flux ripple also doubles, which means F sub, that is the RMS value of stator flux ripple in a sub-cycle, also doubles. So that means current or stator flux ripple doubles. That means current will have more distortion. If you drop the switching frequency by half, which means if you double the sub-cycle interval, so that will double the RMS value of stator flux ripple, which means it will double the RMS value of current ripple. Okay. On the other hand, if you make this switching frequency half, if you double the switching frequency, so another observation is that if switching frequency is doubled, अब हम switching frequency double कर रहे हैं, अगर मैं switching frequency double कर रहा हूँ, what will happen to TS? TS will be halved. TS half हो जाएगा. So TS is halved. And since F sub is directly proportional to TS, F sub also reduces by 1/2. So that means RMS value of stator flux ripple is also halved. So current ripple is also halved. So that means current will have a better harmonic profile. Distortion will be reduced by 1/2, half. Fine. So that means switching frequency has a very important role in deciding about the stator flux ripple or current ripple. So higher the switching frequency, smaller is TS, and smaller is TS, smaller is F sub. Smaller F sub means smaller current ripple. But you cannot go for very, very high switching frequencies. The switching frequency will be determined by two factors. Number one, the type of power semiconducting device which you are using, its switching capability, and number two, switching power losses which are allowed in your system. Okay. Now let us take our discussions forward. I will write again this equation for RMS value of stator flux ripple over a sub-cycle, that is F sub. It is equal to C naught, which is a function of alpha, into Vref square, plus C1, which is also a function of alpha, into Vref, that is rotating reference vector Q, plus C2, which is also a function of alpha, into Vref raised power 4 whole raised power 1/2 into TS. Same equation I am writing. As I just few moments back told you that these terms C0, C1 and C2, they are different for different switching sequences. For example, C0 will have one value for switching sequence 0, 1, 2, 7. It will have different value for switching sequence 0, 1, 2. It will have different value for switching sequence 0, 1, 2, 1. This is the conventional switching sequence. This is bus clamping switching sequence. This is double switching clamping sequence or advanced bus clamping switching sequence. We already discussed these in previous lectures. Okay. Similarly, C1 will be different for different switching sequences. For example, C1 will have one value for conventional switching sequence 0127. It will have a different value for bus clamping switching sequence 012, and it will have a different value for advanced bus clamping switching sequence 0121, which is also called double switching clamping sequence. In a similar way, you will find that C2 parameter or C2 will have different value for conventional space vector switching sequence or conventional switching sequence 0127. It will have a different value for bus clamping switching sequence 012, and it will have a different value for double switching clamping sequence or advanced bus clamping sequence 0121. So this is called C0 sequence. This you can call as C1 sequence, and this you can call as C2 sequence. SEQ means switching sequence. So for different types of switching sequence, for example, this is conventional switching sequence. It is used in conventional space vector PWM. This is bus clamping switching sequence. It is used in space vector based bus clamping techniques or discontinuous PWM techniques. And this is double switching clamping sequence, which is used in space vector based advanced bus clamping techniques. So for conventional space vector PWM, for space vector based bus clamping technique, PWM technique, and for space vector based advanced bus clamping technique, different switching sequences are there, and C0, C1 and C2 will have different values. Okay, so now let us try to understand how the switching sequence changes the value of these coefficients C0, C1, C2, and how it affects the stator RMS value of stator flux ripple. That will be our now main focus. Before we do that, let's have a recap of some switching sequences. For example, we have conventional switching sequence, which is used in conventional space vector PWM technique. Within brackets I will write conventional SVPWM, that is conventional space vector PWM technique. Let us take sector 1. In sector 1, what is the switching sequence? 0127 and then 7210. This is in one subcycle, this is in another subcycle in sector 1. Okay, so it is something like this. This is my null vector 0 with switching sequence minus minus minus. This is another null vector 7 with switching sequence plus plus plus. This is active vector 1 with switching sequence plus minus minus. This is active vector 2 with switching sequence plus plus minus, and my reference vector will be somewhere here. This is VREF, rotating reference vector at an angle of spatial angle of alpha. Now, when we use conventional space vector PWM technique, it uses conventional switching sequence 0127 in one subcycle and then in reverse order in another subcycle 7210. So let us consider this subcycle. We start with 0. So for time interval tz by 2, null vector 0 is applied. Then for time interval t1, active vector 1 is applied. Then for time interval t2, active vector 2 is applied. And then for time interval tz by 2, null vector 7 is applied. So 0 is applied for tz by 2, 1 is then applied for t1, 2 is applied for t2, and 7 is applied for tz by 2 again. And then in the reverse order 7210, null vector 7 is applied again for time interval tz by 2, and then we apply active vector 2. So it goes in the reverse direction. After applying null vector 7 for time interval tz by 2, active vector 2 is applied for time interval t2 dash. Then active vector 1 is applied for time interval t1 dash. Then active vector null vector 0 is applied for time interval tz dash by 2 again. So therefore, when we move from null vector 0 to active vector 1, which phase switches? So R is here minus, R phase is plus. So R phase switches. When we move from active vector 1 to active vector 2, either in this direction or in reverse direction, which phase switches? You can see Y is minus here, it is plus here. So Y phase switches. And when we move from active vector 2 to null vector 7 or null vector 7 to active vector 2 in either direction, which phase switches? B phase is minus here, it is plus here, so B phase switches. So none of the phases gets clamped to positive or negative DC bus. There is all the three phases equally switch. R phase switches, then Y phase switches, then B phase switches, then in the reverse order. So this is conventional switching sequence 0127, 7210, which is used in conventional space vector PWM technique. Okay, fine. Now let us see space vector based bus clamping technique or discontinuous PWM technique. For that purpose, we have two clamping sequence. We will first of all discuss clamping sequence 1. Clamping sequence 1, which is 012 to 10. Okay, let us try to understand this. Again, we have null vector 0 here, minus, minus, minus. We have null vector 7, plus, plus, plus. Then we have active vector 1, plus, minus, minus switching sequence. We have active vector 2 with switching sequence, plus, plus, minus. And time averaging of this will generate a reference vector Vref, okay, which is having which is at any instant of time is having a spatial angle alpha. Fine. Now 012 means for time interval tz, full time interval tz. Only in this case only one null vector is applied, only 0. 7 is not applied. That's why it's called clamping sequence. So for entire time 0 time interval tz, null vector 0 is applied. Then we apply null vector 1 for time interval t1. So we move from 0 to 1. Then we apply null vector, active vector 2. First null vector 0 is applied for time interval tz. Then active vector 1 is applied for time interval t1. Then active vector 2 is applied for time interval t2. So this is 0, 1, 0, 1, 2. And then we move in the reverse direction. 2, 1, 0. That means active vector 2 is applied for time interval t2 dash. Then active vector 1 is applied for time interval t1 dash. Then null vector 0 is applied for time interval tz dash. Okay. The null vector 7 is not applied at all. So therefore when we move from null vector 0 to active vector 1 or active vector 1 to null vector 0 in either direction, which phase switches? R phase is minus here, it is plus here, so R phase switches. Similarly, when we move from active vector 1 to active vector 2 or vice versa, which phase switches? Y is minus here, Y is plus here, so Y phase switches. And what about B phase? B phase does not switch at all. B is minus here, it is minus, it is minus. So B phase is clamped to negative DC bus. This is clamping switching sequence. Okay, we already know it. This is clamping sequence 1. This clamping sequence 1 results in clamping of different phase legs to negative DC buses. For example, for sector 1, for this switching sequence, it clamps B phase to negative DC bus. In other sectors, it will clamp other phase legs to negative DC bus. Okay, this is clamping sequence 1. What about second clamping sequence? So clamping sequence 2. In clamping sequence 2, instead of using null vector 0, we use active vector 7. So it is 7 to 1, 7 to 1, 1 to 7. This is the switching sequence. Okay, 7 to 1, 1 to 7. Okay. Let us quickly draw space vector diagram in sector 1. And this is null vector 0 with switching sequence minus, minus, minus. And this is null vector 7 with switching sequence plus, plus, plus. This is active vector 1 with switching sequence plus, minus, minus. This is active vector 2 with switching sequence plus, plus, minus. And this is our time averaging of the null vector, active vector, null vector 7, active vector 1 and active vector 2. Their time averaging generates a reference vector Vref, which is having a spatial angle alpha. Now what is the switching sequence? 7 to 1. That means we start with null vector 7. Here only null vector 7 is applied. 0 null vector is not applied. So null vector 7 is applied in first subcycle for time interval tz. and then active vector 2 is applied. So we move from null vector 7 to active vector 2. Then we sit here for time interval t2, then active vector 1 is applied for time interval t1. So, okay. Then in the reverse order, 1 2 7, that means we will sit here at active vector 1 for time interval t1 dash, then we will go from active vector 1 to active vector 2, stay there for time interval t2 dash, and we will go from active vector 2 to null vector 7, stay there for tz dash. Okay. So therefore, when we move from null vector 7 to active vector 2 or vice versa, which phase switches? You can see B is plus here, B is minus here. So B phase switches. And similarly, when we move from active vector 2 to active vector 1 or vice versa, which phase switches? Y is plus here, Y is minus here. So Y phase switches. What about R phase? R phase does not switch at all. It's plus, R is plus here, R is plus here. So that means R phase is clamped to positive DC bus, R plus. So this is another clamping sequence. So whenever you use null vector only, it will cause negative DC bus clamping. And if you use null vector 7, it will cause positive DC bus clamping. Okay. We have already discussed in details these different clamping techniques. Okay. So after doing this, we will quickly have a recap of double switching clamping sequence, that is advanced bus clamping sequence. I will write here double switching clamping sequence. Here also we have two sequences, sequence 1 and sequence 2. Sequence 1 is 0 1 2 1 dash 1 2 1 0. In this case, one phase is clamped to negative DC bus, another phase switches once, and the third phase switches twice. That's why it's called double switching clamping sequence, and it gives rise to space vector based advanced bus clamping technique. This is advanced bus clamping technique. Okay, let us draw it in sector 1. We will try to understand it in sector 1 with the help of space vector diagram. This is null vector 0 with switching sequence minus minus minus. This is null vector 7 with switching sequence plus plus plus. Active vector 1 with switching sequence plus minus minus. Active vector 2 with switching sequence plus plus minus. And time averaging of null vector and active vectors generates a reference, rotating reference vector, Vref, as you can see. Now, what is the double switching clamping sequence here? It's sequence 1 and it is 0 1 2 1 in one subcycle. That means we start with null vector. Here also we use only one null vector, 0 in both subcycles. 7 is not used. So this will also result in clamping of one phase leg to negative DC bus. Anyway, we start with null vector 0. Null vector 0 is applied for entire time interval Tz. Then move from null vector 0 to active vector 1. Stay at active vector 1 for time interval T1. T1 by 2. Then we move from active vector 1 to active vector 2. Stay there for time interval T2. Then we move back from active vector 2 to active vector 1. Stay there for T1 by 2. Okay. Like this. Null vector 0 to active vector 1 for time interval T1 by 2. Then active vector 1 to active vector 2. Here we are for time interval T2. Then active vector 2 to active vector 1 again for time interval T1 by 2. So this is 0 1 2 1. This completes one subcycle. In another subcycle, we start with active vector 1. We are already at active vector 1. We have to stay there for T1 dash by 2 time again. So we are there. Then we move from active vector 1 to active vector 2. Stay there for time interval T2 dash. Then we move back from active vector 2 to active vector 1. Stay there again for time interval T1 dash by 2. And then we move from active vector 1 to null vector 0. Stay there for time interval Tz dash. That completes second subcycle, and that completes this switching sequence. Now we can see when we move from null vector 0 to active vector 1, or we move in the reverse direction, that is 1 to 0, which phase switches? R is minus here, R is plus here, so R phase switches. Similarly, when we move from active vector 1 to active vector 2 or 2 to 1, Y phase switches. Y is minus here, Y is plus here. Which phase does not switch? B is minus here, B is minus here, B is minus here. So B phase is clamped to negative DC bus. And this is double switching clamping sequence, because you can see Y phase switches twice. Y phase switches twice. R phase switches only once. Y phase switches twice. B phase is clamped to negative DC bus. So this is double switching clamping sequence 1, 0, 1, 2, 1, 1, 2, 0, 2, 1, 2, 0, 1, 2, 1, 0. We have another double switching clamping sequence where null vector 7 is used, not null vector 0. Double switching clamping sequence 2, which is also a part of advanced bus clamping technique. This is sequence 2. What is that sequence? That is 7, 2, 1, 2, 2, 1, 2, 7. Here you can see active vector 2 switches twice. Active vector switches only once. And one of the phases is clamped to positive DC bus. Let us try to understand it with the help of space vector diagram. This is null vector 0. This is null vector 7. This is active vector 1. Active vector 2. Time averaging of these two active vectors and this null vector will produce rotating reference vector like this. We start with null vector 7. We are using here only null vector 7. We are not using null vector 0. We stay there for time interval tz. Then we move from null vector 7 to active vector 2. Stay there for time interval t2 by 2. We move from active vector 2 to active vector 1. Stay there for time interval t1. We move back from active vector 1 to active vector 2. Stay there for time interval t2 by 2. That completes one subcycle. In another subcycle, we are starting with active vector 2. We are there for time interval t2 dash by 2. We are going from active vector 2 to active vector 1, staying there for time interval t1 dash. Going back from active vector 1 to active vector 2, staying there again for time interval t2 by 2 dash. And then we are going from active vector 2 to null vector 7, staying there for time interval tz dash. Now when transition is made from null vector 7 to active vector 2 or vice versa, which phase switches? B is plus here, B is minus here. So B phase switches. Similarly, when we move from 2 to 1 or 1 to 2, which phase switches? R is plus here, Y is plus here, Y is minus here. So Y phase switches. So you can see, what about R phase? R is, you can see plus, plus, plus. It is plus. So R phase is clamped to positive DC bus. So therefore, R phase is clamped to positive DC bus. B phase clamps, B phase switches once and Y phase switches twice. So that is about double switching clamping sequence 2. Okay, we have already used these double switching clamping sequences in various types of space vector based bus clamping techniques or discontinuous PWM techniques. We have discussed those techniques in details in a couple of lectures previously. Now, let us try to see what is the effect of these switching sequences on stator flux ripple vector in a subcycle. You may use conventional space vector PWM technique where conventional switching sequence 0, 1, 2, 7, 7, 2, 1, 0 is applied. Or you may use a bus clamping switching sequence 0, 1, 2, 2, 1, 0 or 7, 2, 1, 1, 2, 7. Or you may use double switching clamping sequence 0, 1, 2, 1, 1, 2, 1, 0 or 7, 2, 1, 2, 2, 1, 2, 7. This is conventional switching sequence, this is bus clamping sequence, and this is advanced bus clamping sequence. What is their influence on RMS stator flux ripple? That is we are now going to study that. I'm going to write here influence of switching sequences, influence of switching sequences on RMS stator flux ripple, RMS stator flux ripple over a subcycle. We are going to discuss that. Okay, so before I start discussing that, a few points you have to note. Number one, same reference voltage vector is resulted. Same rotating reference voltage vector. What does that mean? Whatever switching sequence you use, whether you use conventional switching sequence, bus clamping switching sequence, or double switching clamping sequence, rotating reference, same rotating reference will be generated by all the three, all types of these switching sequences. It's not going to change. And then second point is that instantaneous applied voltage, instantaneous applied voltage error, voltage error vector differs with switching sequence, with instantaneous applied voltage vector. It's not error. Instantaneous applied voltage vector differs with switching sequence. That is clear because in one switching sequence you are applying one voltage vector. In another switching sequence you may be applying different voltage vector. So for different switching sequences, different voltage vectors are applied at an instant of time. Okay, so it differs with switching sequence. Then we can write instantaneous error voltage vector also differs with switching sequence. With switching sequence. You'll see it in a minute's time. Error voltage vector with one switching sequence may be something, and with another switching sequence it may be something different. Okay, and finally stator flux ripple vector, stator, which is important. This last point is very important. Stator flux ripple vector or current ripple vector, because this stator flux ripple vector is a measure of current ripple vector, or current ripple vector is different for different switching sequences, for different switching sequences. Let us try to understand how the stator flux ripple vector is different for different switching sequences. It will be very interesting to study this phenomenon now. Okay. Let us now start with conventional let us start with clamping sequence. Okay, I will write here stator flux ripple vector, and let us use clamping sequence, both the clamping sequences. We are using bus clamping sequences. First 0 1 2 1 and then 0 1 2 and 7 2 1. In this is bus clamping sequence, this is also bus clamping sequence, but difference is that here null vector 0 is applied only and here null vector 7 is applied only. This bus clamping sequence will result in clamping of one phase leg to a negative DC bus, and this will result in clamping of phase legs to positive DC bus. That's it. Well, let us try to see if the two clamping sequence produce same results. I mean, they produce same rotating reference vector, they produce same clamping, each phase leg gets clamped to say negative DC bus or positive DC bus for equal interval of time, then what is the difference between the two switching sequences in terms of stator flux ripple vector? That's our point of discussion here. So this we can understand with the help of the space vector diagram. I will again draw space vector diagram. This is alpha axis and this is my beta axis. This is space vector diagram I am trying to draw. This is my, for example, null vector 0, minus, 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 and this is null vector 7, plus, plus, plus. Now, this is, for example, active vector 2 with switching sequence plus, plus, minus. And this is my, for example, this is my active vector 1. It's switching sequence plus, minus, minus. The time averaging of null vector and two active vectors will produce a reference vector. Let me show that reference vector somewhere here. So this is my reference vector. And this is alpha. In this case, alpha is less than 30 degrees. I am deliberately making alpha less than 30 degrees. This total angle between active vector 1 and active vector 2 in sector 1, this is sector 1, this angle is 60 degrees. Okay? And I am making this is my reference vector, Vref. I am making this reference vector spatial angle alpha less than 60 degrees deliberately. I'll explain it why I am making it less than 30 degrees. Please bear with me. It will be clear to you in a minute's time. Then we already know this is our q-axis. This is our q-axis. Q-axis is along Vref. And this is my d-axis. This is d-axis. Let us first of all use switching sequence 0, 1, 2. Okay. When null vector 0 is applied, this is the error vector. This is error vector V, जिसको हम V error कहते हैं. When active vector 1 is applied, this is what is desired and this is what we apply. So this is the error vector V error. When active vector 2 is applied, okay, this is active vector 2. What is desired is Vref, but what we are applying is this. So this is error vector V error. Then we already know how do you find stator flux ripple. You find stator flux ripple by integrating these error voltage vectors. For example, your error voltage vector when null vector is applied is this line, this dashed line. When you integrate it, you move from the origin, so you move in this direction. Okay, since this null vector 0 is applied for entire time interval tz, because we are not using null vector 7, we are using only null vector 0. It's not applied for tz by 2, it's applied for entire time interval tz. So therefore, integrating this error voltage vector, okay, it will result in stator flux ripple, which will grow. Integration of this error voltage vector when null vector 0 is applied will result in stator flux ripple, which will grow in this direction. So this is when null vector 0 is applied, and it is applied for time interval tz. ये मेरा tz है for entire time interval tz. And you can see this error vector is in this direction, and we already know that this error vector is equal to minus Vref. It is minus Vref. So it is in this direction, minus Vref. So it goes negative, and it reaches maximum negative somewhere here. Here it is maximum negative. After that we apply active vector 1. Now when active vector 1 is applied, this is the error vector. When you integrate this error vector, so you will get stator flux ripple, which will move in this direction parallel to this line. Okay, so let us start tz. So we will have vector 1. So this is when active vector 1 is applied, and you can see the stator flux ripple grows in this direction parallel to this error vector. Okay, fine. And what is the time here? Say tz plus t1. And then we apply active vector 2. When active vector 2 is applied, the error vector is this line, dashed line. And when we integrate this error vector, we get stator flux ripple. And that stator flux ripple will grow in this direction, and that will be parallel to this. So that will be parallel to this. It will इसके parallel जाएगा, it will go parallel to this, वापस जाएगा. This is when active vector 2 is applied, and this ends my subcycle TS. So this is 0, 1, 2. 0, then 1, then 2. Okay. Now let us apply clamping sequence 7, 2, 1. Instead of applying 0, 1, 2, now I will apply 7, 2, 1. Now when 7 is applied, 7 is also a null vector like 0. When 7 is applied at that time also, you know, your error vector is this, and it is equal to minus VREF. So that means when 7 is applied, my stator flux ripple is same as when 0 was applied. For 7 is applied for time interval Tz. Okay, it is same, exactly same. It does not change. And then after 7, which vector is applied? Active vector 2 is applied, not active vector 1. Active vector 2 is applied. So error vector is this. When I integrate this, I get stator flux ripple parallel to this, something like this. इसके parallel एक line में draw करूँगा. I will use red pen for this. So this is when active vector 2 is applied. And what is this time here? This is Tz plus T2. And after that we apply active vector 1. When active vector 1 is applied, this is the error voltage vector. And integration of this error voltage vector gives stator flux ripple, which will grow in this direction parallel to this. Then active vector 1 is applied, and that completes our subcycle. Okay, and this is our stator flux ripple vector psi tilde. Here flux ripple vector. When switching sequence, clamping sequence 0, 1, 2 is used, this psi tilde moves like this, you tracing this triangle path. When 0 is applied, it moves like this. When active vector 1 is applied, it moves like this. When active vector 2 is applied, it moves like this, goes back to origin. And when this switching sequence, clamping sequence 7 to 1 is applied, first 7 is applied, then psi moves in this direction, psi tilde, then 2 is applied, it moves in this direction, then 1 is applied, it moves in this direction. So यहाँ पे भी आप दिखा सकते हैं, this is psi tilde. Okay. Now this is the stator flux ripple when 0, 1, 2 is applied. Here I will write clamping sequence 0, 1, 2 is applied, and this is the stator flux ripple, the triangle stator flux ripple hai when 7 to 1 clamping sequence is used, right? Now which one is better? You can very clearly see that as far as D components of these flux, stator flux ripples are concerned, D component FD and Q component FQ. D components do not change. For these two switching sequences produce same magnitude of D component of stator flux ripple. But Q components vary. For example, let us take switching sequence 0, 1, 2. When null vector 0 is applied, this is your stator flux ripple, moves here, maximum. Then active vector 1 is applied, so ये कम हो जाता है. It is maximum negative here, so it's at peak value here. Then it decreases, and it decreases very quickly. And then active vector 2 is applied, it goes back to origin. On the other hand, when clamping sequence 7, 2 is applied, first we apply null vector 7. So उस केस में भी ये maximum negative पे पहुंच जाता है. Then we apply active vector 2. When we apply active vector 2, the Q component of stator flux ripple does not decrease, rather it increases. You can see here in this case it decreases. When 0, 1, 2 sequence was used, the Q component is like this, then Q component decreases. ये Q component ये है, इसका Q component कम हो जाता है और फिर 0 हो जाता है. But when 7 to 1 clamping sequence is used, this is null vector, Q component increases. Then when active vector 2 is applied, Q component, unlike this, does not decrease, rather it increases. And then when active vector 1 is applied, the Q component decreases, but it decreases gradually. So therefore, Q component flux ripple is more when clamping sequence 721 is applied as compared to when clamping sequence 012 is applied. Because when 012 clamping sequence is applied, you can see that when active vector 1 is applied, your Q component of stator flux ripple, it quickly decreases and then becomes 0. But when clamping sequence 721 is used, you can see when active vector 2 is used, your Q component of stator flux ripple does not decrease. It does not decrease like this. It rather increases. And then when active vector 1 is applied, it gradually decreases. So therefore, stator flux ripple, Q component of stator flux ripple is higher for 721 clamping sequence than for 012 clamping sequence for alpha less than 30 degrees. Okay, so therefore I can write like this: FQ 721 is greater than FQ 012 for alpha less than 30 degrees. Means if alpha is less than 30 degrees, our rotating reference vector is here. It has made an angle which is less than 30 degrees, say 0 to 30 degrees. Then stator Q component of stator flux ripple vector produced by 721 produced by 721 clamping sequence is higher than the Q component stator flux ripple produced by clamping sequence 012. In other words, or FQ 012 is less than FQ 721 for alpha less than 30 degrees. But if alpha is greater than 30 degrees, I mean if your reference vector is not here, it is somewhere here greater than 30 degrees. For greater than 30 degrees, you can again repeat this exercise. You can again draw this stator flux ripple for 012 and 721, and then you will find that for alpha greater than 30 degrees up to 30 to 60 degrees, the Q axis stator flux ripple produced by 721 clamping sequence is less than that produced by 012 clamping sequence. That is, FQ 721 is less than FQ 012 for 30 degrees less than alpha less than 60 degrees. So this is very important. You have to remember it. So two things we have noticed from here. That means if alpha is less than 60 degrees and you are using clamping sequence 012, then the Q component of stator flux ripple is less than the Q component of stator flux ripple produced by clamping sequence 012 is less than the Q component stator flux ripple produced by clamping sequence 721 for alpha less than 30 degrees. But for alpha greater than 30 degrees, that is 30 less than alpha less than 60 degrees, reverse is true. That is, the stator flux ripple produced by clamping sequence 721 will be less than the stator flux ripple produced by clamping sequence 012. So this is very important. You have to remember this. Okay. With this knowledge, let us see how does it affect various space vector based bus clamping PWM techniques. For this purpose, I will first of all discuss with you space vector based, I will write here, space vector based 60-degree clamping, 60-degree clamp PWM technique. Space vector based 60-degree clamp PWM technique. That's like this. Let's draw the complete space vector diagram. It's already, we know this 60-degree space vector based 60-degree clamp PWM. We have already drawn space vector diagram for 60-degree clamp PWM in one of the earlier lectures. I am reproducing that. This is active vector 1 with switching sequence plus minus minus. This is active vector 2 with switching sequence plus plus minus. This is active vector, this is active vector 3 with switching sequence, this is active vector 3 with switching sequence minus plus minus. This is active vector 4 with switching sequence minus plus plus, opposite of this. Active vector 5 with switching sequence opposite of this. This is plus plus minus, it will be minus minus plus. and active vector 6 with switching sequence opposite of this. Here it is minus plus minus, here it will be plus minus plus. And then we have null vector 0 with switching sequence minus minus minus, and null vector 7 with switching sequence plus plus plus. Fine. And our reference vector will be rotating in a circular path like this. Then I will divide each sector. This is sector 1, this is sector 2, this is sector 3, this is sector 4, this is sector 5, and this is sector 6. I will divide each sector into 30 degrees. I will split each sector or divide each sector into 30-degree interval each, like this. Similarly, this sector also, I will bifurcate it into 30 degrees each. Fine. If you remember, you just go back what I have already learned in one of the previous classes. If you have to implement space vector based 60-degree clamp PWM, and you have to clamp each phase leg to positive DC bus and negative DC bus in the middle of half cycle, for 60 degrees. Then what should be the switching sequence? If you remember, the switching sequence should be like this. In sector 1, we start with 721 and 127. Okay, 7, 2, 1. And then this is in first 30 degrees. In next 30 degrees, it is 0, 1, 2, 0, 1, 2, 2, 1, 0. Okay. Then we move from sector 1 to sector 2. When we move from sector 1 to sector 2, the switching sequence is 032, 032-230. We have already learned these switching sequences. We have discussed these switching sequences for space vector based 60-degree clamp PWM technique in details in one of the earlier lectures. So that's why I am not explaining it again. I hope you have already revised that lecture. You have gone through that lecture and you know that. So this is 032-230. I am rushing now. I'm not moving slow, I'm moving fast. This is 723, 327 switching sequence. Then 741, 147, right? Oh, sorry, this is 743, 347, right? Then 034, 430, right? Then 054, 450, fine. Then 745, 547, then 765, 567, and this is 056, 650. This is 016, 610, and finally 761, 167. Now you can see for this period, for this 30-degree interval, 761, 167, it will result in clamping of R phase to positive DC bus. And for this 30, this is 30 degree, for this 30-degree interval, 721, 12 sequence will again cause clamping of R phase to positive DC bus. That means for this 60-degree interval, R phase will be clamped to positive DC bus. Similarly, you can do it for other phases. Now the question is, this switching sequence is like this. This is our sector 1. Let us concentrate on sector 1. This is my sector 1. I will mark it with a red pen just to differentiate it. This is my sector 1. In sector 1, I am starting with switching sequence 721 in first 30-degree interval, and in next 30-degree interval, my switching sequence is 012. Just a few moments back, we have seen the influence of these clamping sequences on stator flux ripple. And we have noted that stator flux ripple, Q-axis component of stator flux ripple for 7 to 1 clamping sequences higher than Q-axis component of stator flux ripple for switching sequences, clamping sequence 012 for alpha less than 30 degrees. And Q-axis component of stator flux ripple with clamping sequence 0, 1, 2 is greater than Q-axis ripple, stator flux ripple with clamping sequence 7 to 1 for alpha 30 to 60 degrees. 30 degrees less than alpha less than 60 degrees. So that means in first 30 degrees, when your reference vector is, within this 30 degrees, and if you are using clamping sequence 7 to 1, then it will result in higher, Q-axis stator flux ripple. Because just few moments back we have seen that stator flux ripple, Q-axis component of stator flux ripple with clamping sequence 7 to 1 is higher than Q-axis stator flux ripple with clamping sequence 0, 1, 2 if alpha is less than 30 degrees. And unfortunately, what we are doing in this first 30 degrees, in this sector 1, in first 30 degrees, we are using clamping sequence 7 to 1. So it will result in higher stator flux ripple. And in next 30 degrees, we are using clamping sequence 0, 1, 2. That will also result in higher stator flux ripple. So therefore, this space vector based 60-degree clamp in each sector will result in larger Q-axis stator flux ripple. So therefore, this will result in highest THD of current among all discontinuous PWM techniques. So this will result in highest THD among all discontinuous PWM techniques. Discontinuous PWM techniques means bus clamping PWM techniques. Discontinuous or bus clamping PWM techniques. This is the only way to implement space vector based 60-degree clamp PWM, but it results in large Q component stator flux ripple in this 30-degree interval as well as in 30-degree interval. So therefore, space vector based 60-degree clamp PWM technique, or in general 60-degree clamp PWM technique, will result in highest THD among all bus clamping or among all discontinuous PWM techniques. Fine. Let us now discuss 30-degree clamp PWM. Quickly, space vector based 30-degree clamp PWM technique, which is one of the special cases of split clamp PWM technique. Again, we will draw the space vector diagram. This is active vector 1. This is active vector 2. This is active vector 3. This is active vector 4. This is active vector 5. This is active vector 6. And these are two null vectors, 0 and 7. Fine. So this is our space vector diagram. And our rotating reference vector will be rotating in circular trajectory like this. This is my sector 1. This is sector 2. This is sector 3. This is sector 4. This is sector 5. And this is sector 6. Okay. So I will bifurcate each sector into equal 30-degree intervals, 30 degrees. I will divide it into equal 30 degrees. 30 degrees similarly, just 30 degrees. And here also. Now in 30-degree clamp PWM technique, if you see, first sector, sector 1, we do not start with null vector 7, we start with null vector 0. So when I use 0, then I have to use active vector 1 first, then active vector 2, and in the reverse order 2, 1, 0. This is the clamping sequence. And this is for first 30 degrees interval. Then for next 30-degree interval, 7 to 1, 1 to 7. This is sector 1. So similarly for other sectors, this sector 2, 7 to 3, 3 to 7, and 0, 3 to 30, then 0, 3, 4, 4, 3, 0, and 7, 4, 3, 3, 4, 7, right? Then 7, 4, 5, 5, 4, 7, right? Then 0, 5, 4, 4, 5, 0, then 0, 5, 6, 6, 5, 0, then 7, 6, 5, 5, 6, 7, then 7, 6, 1, 1, 6, 7, and finally 0, 1, 6, 6, 1, 0. We have seen the influence of bus clamping sequences, clamping sequences on stator flux ripple few moments back, and we found that the q-axis component of stator flux ripple for clamping sequence 0, 1, 2 is less than the q-axis stator flux ripple produced by clamping sequence 7 to 1 for alpha less than 30 degrees. And q-axis stator flux ripple produced by 7 to 1 clamping sequence is less than q-axis stator flux ripple produced by clamping sequence 0, 1, 2 for alpha greater than 30 degrees. That is 30 degrees less than alpha less than 60 degrees. And luckily, this is holding true here. If you take sector 1, for example, let us take this sector 1. This is my sector 1. In first 30 degree interval, which clamping sequence I am using? 0, 1, 2. And the 0, 1, 2 for alpha less than 30 degrees, it produces less stator flux, q-axis stator flux ripple. And in next 30 degree interval, which clamping sequence I am using? 7 to 1. And that also produces less clamping, less q-axis stator flux ripple. So therefore, the 30 degree clamp PWM technique produces, lowest q-axis stator flux ripple, and hence it produces the lowest THD of the current among all bus clamping techniques. So therefore, it produces lowest THD among all discontinuous PWM techniques, or among all bus clamping PWM techniques. Bus clamping PWM techniques. So therefore, the scenario with 60 degree clamp PWM technique is worst in terms of THD, and it is best in terms of THD for 30 degree clamp PWM. Fine. So therefore, we have seen the influence of the two clamping sequences on stator flux ripple, and we have seen their effect or influence on two types of discontinuous PWM techniques: 60 degree clamp PWM technique and 30 degree clamp PWM technique. Let us quickly go to double switching stator. We are now going to discuss stator flux ripple. Stator flux ripple vector using double switching clamping sequence. Double switching clamping, which is also called advanced bus clamping. Advanced bus clamping sequences. And what are those two sequences? 0, 1, 2, 1 and 7, 2, 1, 2. These are two double switching clamping PWM techniques, or two advanced bus clamping PWM techniques. Let us see their effect on stator flux ripple. It will be again clear to you with the help of space vector diagram. This is alpha, this is beta. Fine. This is my active vector 2 plus plus minus. I will again take reference. This is null vector 0 minus minus minus. This is null vector 7 plus plus plus. I will again take V reference, say somewhere here. This is my V reference. This is V ref. And this is active vector 1 with switching sequence plus minus minus, and this is active vector 2 with switching sequence plus plus minus. When null vector 0 or null vector 7 is applied, the error vector is in this direction. This is VR. When active vector 1 is applied, this is the error vector VR. When active vector 2 is applied, this is the error vector VR. This is now our Q axis. Now I will draw the stator flux ripple separately for two clamping sequences. First for 0, 1, advanced bus clamping sequence 0, 1, 2, 1. So for 0, 1, 2, 1, this is my D axis. This is Q axis. First null vector 0 is applied and it is used for entire time interval Tz. So this is null vector 0. It's applied for entire time interval Tz. यहाँ से यहाँ तक. से यहाँ से यहाँ तक. Then active vector 1 is applied. It's applied for time interval T1 by 2. It's not applied for full time interval T1 because ये इसकी double switching होती है. It's applied twice. This active vector 1 is applied twice. Here for T1 by 2, here for T1 by 2. T1 by 2 means, so the stator flux ripple will move parallel to this error vector when active vector 1 is applied. It's applied for time interval T1 by 2. So this time is Tz plus T1 by 2. Then which vector is applied? Active vector 2 is applied. It's applied for time interval T2 and stator flux will move parallel to this line. Move parallel when active vector 2 is applied. So here time is Tz plus T1 by 2 plus T2. And then active vector 1 is again applied for time interval T1 by 2 and therefore my stator flux ripple will move again parallel to this line to come down. Active vector 1 is again applied. That's it. Okay. Null vector first applied, then active vector 1, then active vector 2, then again active vector 1. This is if I use this switching sequence 0, 1, 2, 1. What about if I use switching sequence 7, 2, 1, 2? उसके लिए I will use another D axis. मैं यहाँ एक और parallel D axis use करूँगा. First null vector 7 is applied and this null vector 7 is applied for entire time interval Tz. So this is null vector 7. It's applied for time interval Tz. Then active vector 2 is applied, not 1. 2. So therefore my flux ripple will move, it will grow parallel to this vector, error vector, when active vector 2 is applied. So it will move like this for time interval T1 by 2. So this is when 2 is applied. Okay, it is applied for Tz plus T2 time. Then active vector 1 is applied. When active vector 1 is applied, my error voltage vector at that time is this. And stator flux, when I integrate this error voltage vector, it will give me stator flux ripple, which will move, which will grow parallel to this line. It will move parallel to this line. When active vector 1 is applied, and this time interval is Tz plus, here it is T2 by 2. Tz plus T2 by 2 plus T1. And then active vector 2 is again applied for time interval T2 by 2. And therefore, when active vector 2 is applied, error voltage vector is this. Integrating this will give stator flux parallel to this. So this is active vector 2 is applied again for time interval T2 by 2. Okay, so this is the stator flux ripple when double switching clamping sequence or advanced bus clamping sequence 0, 1, 2, 1 is applied. And this is the stator flux ripple when double switching clamping sequence 7, 2, 1, 2 is applied. 7, 2, 1, 2. Do you find any difference between the two? As far as D-axis ripple is concerned, D-axis ripple is small in both the cases, is lowest for both sequences. The reason being because see it is this T1 by 2, it is not going, when I apply active vector 1, I apply it only for time interval T1 by 2, not for entire time interval T1. So D axis यहीं पे खत्म हो जाता है, then it goes up. Similarly, when active vector 1 is applied, it's applied for small time interval t1 by 2. Sorry, active vector 2, when active vector 2 is applied, it's applied for small time. It's not applied for entire time period t2. It's applied for t2 by 2. So d-axis ripple is low in both the cases. However, q-axis ripple is slightly better for this switching sequence. You can see q-axis ripple sharply decrease हो जाता है. In this case, q-axis ripple sharply decrease नहीं होता है, पहले बढ़ता है फिर decrease होता है. So as far as q-axis ripple of the two clamping sequences is concerned, this switching sequence gives slightly better q-axis ripple as compared to this switching sequence. So therefore, I can say that q-axis ripple with switching sequence 0, 1, 2, 1 is less than q-axis ripple with switching sequence 7, 2, 1, 2 for alpha less than 30 degrees. And on the contrary, if my reference vector is not here, it's somewhere here, then alpha is greater than 30 degrees. Then in that case, q-axis ripple with switching sequence 7, 2, 1, 2 is less than q-axis ripple with switching sequence 0, 1, 2, 1 for alpha greater than 30 degrees but less than 60 degrees. Okay, let us apply this knowledge now to advanced bus clamping PWM techniques. We have two types of advanced bus clamping techniques. First of all, I will draw advanced bus clamping PWM. Advanced bus clamping PWM 1. It's something like this. Active vector 1. I'm drawing the space vector diagram. This is active vector 2. This is active vector 3. This is active vector 4. This is active vector 5. And this is active vector 6. This is null vector 0 and another null vector 7. This is my sector 1. Similarly, these are other sectors. Okay, so I am bifurcating each sector into 30-degree intervals like this, as I have been doing for other sequences a few moments back. Okay, in advanced bus clamping PWM technique, we start with sector 1 and switching sequences 7, 2, 1, 2, then 2, 1, 2, 7. And the next 30 degrees it is 0, 1, 2, 1, 1, 2, 1, 0. Okay, and then it is 0, 3, 2, 3, 3, 2, 3, 0. And then it is 7, 2, 3, 2, 2, 3, 2, 7. So go on like this: 7, 4, 3, 4, 4, 3, 4, 7. We have already discussed these clamping sequences when we discussed advanced bus clamping techniques. So I am just writing these sequences. You know how to get these sequences. This is 0, 3, 4, 3, 3, 4, 3, 0. This is 0, 5, 4, 5, 5, 4, 5, 0. This is 7, 4, 5, 4, 4, 5, 4, 7. Then 7, 6, 5, 6, 6, 5, 6, 7. Then 0, 5, 6, 5, 5, 6, 5, 0. And then 0, 1, 6, 1, 1, 6, 1, 0. And finally 7, 6, 1, 6, 6, 1, 6, 7. That's it. Few moments back we found that the q-axis ripple for switching sequence 0, 1, 2, 1 is less than the q-axis ripple, q-axis stator flux ripple produced by switching sequence 0, 2, 1, 2 for alpha less than 30 degrees. And we also found that Q-axis stator flux ripple produced by switching sequence 7212 is less than the Q-axis stator flux ripple produced by the double switching clamping sequence 0121 if alpha is greater than 30 degrees. But in first 30 degrees, which double clamping sequence I am using? I am using 7212. I am not using 0121. So 7212 will give higher stator flux, Q-axis stator flux ripple. In next 30 degrees, which clamping sequence gives low ripple? 7212, but we are using 0121, so it will result slightly higher stator flux ripple. So therefore, this advanced bus clamping PWM technique, this type of technique, this will give highest THD among all the advanced bus clamping PWM techniques. Okay. Let us quickly go to advanced bus clamping PWM 2. Advanced bus clamping PWM 2. We have to draw the space vector diagram again. Active vector 1, then active vector 2, then active vector 3, then active vector 4, then active vector 5, then active vector 6, null vector 0, and null vector 7. Okay, now in sector 1, this is my sector 1. In advanced bus clamping PWM 1, we started with 7212. So in advanced bus clamping PWM 2, I will not start with 7212. I will start with 0121, then 1210, then 7212, 2127. And similarly, you can repeat it for other sectors. Let us concentrate on one sector. So we can write the clamping sequences, double switching clamping sequences for all other sectors. Okay, we have already told you how to do that. Now again, we have found few moments back that the Q-axis stator flux ripple produced by double switching clamping sequence 0121 is less than the Q-axis stator flux ripple produced by the sequence 7212 for alpha less than 30 degrees. And Q-axis stator flux ripple produced by clamping sequence 7212 is less than Q-axis stator flux ripple produced by switching sequence 0121 for alpha greater than 30 degrees. And luckily, you can see in first 30 degrees, which double switching clamping sequence I am using. We are using 0121. And this produces less stator flux ripple, Q-axis stator flux ripple. And in next 30 degrees, we are using clamping sequence 7212. That also gives, for alpha greater than 30 degrees, that also gives less Q-axis stator flux ripple. So therefore, this advanced bus clamping PWM 2, this type of double clamping sequence, this will give highest THD. This will give lowest THD among all the advanced bus clamping techniques that we discuss. Okay, that we have discussed. Okay, so that's it. So therefore, we have seen how different switching sequences, how they result in different stator flux ripple, how stator flux ripple is influenced by different switching sequences. We have seen that space vector based 60-degree clamp or 60-degree clamp PWM technique gives highest THD among all the bus clamping techniques, and 30-degree clamp PWM technique gives lowest THD among all the bus clamping techniques. Similarly, advanced bus clamping PWM 1 gives highest THD, and advanced clamping PWM 2 gives lowest THD, same way. Now let us try to compare, the conventional and clamping sequences as far as these stator flux ripple is considered. I will write here stator flux ripple vector produced by conventional and clamping sequences. Clamping sequences. For example, conventional sequences 0, 1, 2, 7 and bus clamping sequences 0, 1, 2. Let us try to compare the two. I mean, we are not now comparing clamping sequence, one clamping sequence with another clamping sequence. I am comparing clamping sequence with conventional switching sequence. Okay, this will be clear again with space vector diagram. This is active vector 1, for example, this is null vector 0, this is null vector 7. This is, for example, active vector 2. This is reference vector vref. This is my active vector v1, switching sequence plus minus minus, and this is active vector 2 here. This is active vector 2, switching sequence plus plus minus. Right? Now, this is my q axis, and let us say this is somewhere here I have d axis. This is d axis. Let us first of all use conventional switching sequence, conventional space vector based switching sequence 0, 1, 2, 7, which is also called conventional switching sequence. Null vector 0 is used for time interval tz by 2, 0 is used for time interval tz by 2, 7 is also used for time interval tz by 2. So 0 is used for time interval tz by 2. यहाँ से यहाँ तक. And 0 error vector is this. When you then null vector 0 is applied, this is the error voltage vector. When this is integrated, it gives stator flux ripple, which grows in this direction like this. Okay. Then active vector 1 is applied. When active vector 1 is applied, the error voltage vector is this. Integration of this gives stator flux ripple vector, which is parallel to this. Okay. So active vector 1 is applied. So this is active vector 1. Then this active vector 1 is applied for time interval t1. Then active vector 2 is applied. When active vector 2 is applied, we have stator flux ripple which moves parallel to this, like this. When 2 is applied, and then null vector 7 is applied for same time period tz by 2. This is null vector 7. So this is switching sequence 0, 1, 2, 7. This is conventional switching sequence. What if we are not using conventional switching sequence? We are using bus clamping sequence 0, 1, 2. Okay. In bus clamping sequence, only null vector 0 is used, whereas in conventional switching sequence, null vector 0 and 7 both are used. They are used for time intervals tz by 2, tz by 2, as I have already told you, tz by 2, tz by 2. But in bus clamping sequence 0, 1, 2, only one null vector, say in this case null vector 0 is used, and this 0 is used for entire time interval tz. So यहाँ तक आप null vector 0 apply करते हैं, यहाँ तक. Then active vector 1 is applied. Active vector 1 is applied, so my stator flux ripple grows parallel to this, like this. Okay, parallel जाएगा नीचे. Okay. Then active vector 2 is applied. When active vector 2 is applied, my stator flux ripple vector will move parallel to this, like this. So sub-cycle complete हो गया. So therefore, this is the stator flux ripple when clamping sequence 0, 1, 2 is used. This black triangle shows stator flux ripple when conventional this space vector switching sequence or conventional switching sequence 0, 1, 2, 7 is used. And this red color triangle shows the stator flux ripple when clamping sequence 0, 1, 2 is used. Compare the two. As far as their D components are concerned, D components have almost same peaks, but Q components are different. You can see when 0, 1, 2, 7 conventional switching sequence is used, the Q axis ripple vector grows only up to this point, okay, because this time interval is tz by 2 only, and then it decreases, becomes positive, and then goes and becomes 0. On the other hand, when bus clamping sequence 0, 1, 2 is applied, 0 is used for entire time interval tz, and it is there for larger time, so the error, the current, flux ripple is very large. It's almost double than this, which was produced by conventional switching sequence 0, 1, 2, 7. The q-axis ripple, this is the q-axis ripple when null vector 0 is applied for entire time interval tz. It is double than that produced by switching sequence 0, 1, 2, 7. And then it decreases, and it also finally goes to 0. But you can see the peak of the ripple is double than peak of the ripple, as peak of the ripple, q-axis ripple produced by clamping sequence 0, 1, 2 is double than that produced by conventional switching sequence 0, 1, 2, 7. So that is why clamping sequence PWM or bus clamping PWM, I should write here bus clamping PWM techniques, they produce higher stator flux ripple and hence higher THD. But I have already told you, in bus clamping technique, each bus or each phase leg is clamped to a bus for 120 degrees. So therefore, if FC is your carrier frequency, the effective switching frequency is only 2 by 3 of carrier frequency. Whereas in conventional, space vector PWM, switching frequency is same as carrier frequency. In bus clamping PWM techniques, the switching frequency is only 2 by 3 of carrier frequency. And if you want the switching frequency same as that in conventional space vector PWM, then you have to increase this carrier frequency by a factor of 3 by 2. That is by a factor of 1.5. So that this 2 and 2 goes, 3 and 3 goes. Okay. So that means the carrier frequency has to be raised by 1.5 FC so that the effective switching frequency is same as that in conventional space vector PWM. And when we increase the carrier frequency by 5 times, I've already told you while discussing the harmonic spectrum of voltages. So every harmonic frequency component gets shifted towards the right. So therefore, my first predominant harmonic will not be at carrier frequency, but it will be at carrier frequency. It will not be at FC. It will be at FC 1.5 FC and its sidebands. And 1.5 FC is higher than FC, so therefore its amplitude is less, and it will produce the current in the stator winding of induction motor, whose magnitude is less than as compared to carrier frequency FC. Because here carrier frequency has increased, it's not FC, it is 1.5 FC. So we know that current is proportional to Vn by N, since harmonic order has increased. So nth harmonic order of current also reduces. So THD of the current decreases. So therefore, although stator flux ripple here shows that flux ripple, q-axis flux ripple, and hence distortion produced by bus clamping technique is more than produced by conventional space vector based PWM technique. But that is true if your switching frequency is 2 by 3 times FC. If you want your switching frequency same as that in conventional space vector PWM, then your FC has to be equal to FC dash has to be 1.5 times FC. So that increases the harmonic order, and hence that reduces the stator flux ripple, and that reduces the THD of the current. So therefore the THD of the current, instead of increasing, it will decrease with advanced bus clamping technique. For example, using the switching sequence, clamping sequence 0, 1, 2, or you may use 7, 2, 1. Okay. So in a similar way, we will compare conventional switching sequence with advanced bus clamping switching sequence or double switching clamping sequence. I will write here stator flux ripple vector conventional and double switching conventional and double switching clamping sequences. That is, conventional switching sequence is 0, 1, 2, 7, and double switching clamping sequence or advanced bus clamping sequence, we may use 0, 1, 2, 1, for example. Okay, so again our alpha axis, this is beta axis, and this is null vector 0, this is null vector 7, this is active vector 2, plus plus minus, this is reference vector Vref, this is, say for example, active vector 1, plus minus minus, this is active vector 2, and these are error vectors. This is Vr, this is also Vr, this is also Vr here, sorry. So in order to have the sufficient space, in fact I should use this reference vector, say use reference vector somewhere here. This is Vref, this is active vector 2, this is active vector 1, and this is my Q axis, and this is the D axis. This is the origin. Now when 0, 1, 2, 7 is applied, again 0, 1, 2, 7, 0 is applied for time interval tz by 2, then 1 is applied for time interval t1, then 2 is applied for time interval t2, and then 7 is also again applied for time interval tz by 2. Okay, this is when you use conventional switching sequence 0, 1, 2, 7, which is produced by conventional space vector based PWM technique. And if I use double switching clamping PWM technique, double switching clamping PWM technique or advanced bus clamping PWM technique 0, 1, 2, 1. So it is like this. Here only one null vector 0 is used, and it is there for entire time interval tz. So 0 is for entire time interval tz. Okay, then 1. So when active vector 1 is applied, I will have flux ripple vector which is parallel to this. So this is 1 parallel to this. Then 2 is applied. 1 is applied for time interval t1 by 2. Then 2 is applied for time interval t2. This is 2 is applied. Then 1 is again applied for time interval t1 by 2. 1 is again applied. That's it. So in this case also you can see the peak of the q-axis flux ripple is half as that produced by conventional switching sequence 0, 1, 2, 0, 1, 2, 7 as compared to double switching clamping sequence 0, 1, 2, 1. In other words, the q-axis flux ripple is higher, which is the q-axis flux ripple produced by double switching clamping sequence or advanced bus clamping sequence 0, 1, 2, 1 is higher than that produced by conventional space vector based switching sequence 0, 1, 2, 1. Okay, so does it mean that we should then not use double switching clamping sequences, or we should not go for advanced bus clamping sequences? Because this diagram tells us that the stator flux ripple is higher which is higher stator flux ripple is produced by advanced bus clamping PWM technique than conventional space vector based PWM technique. So we will discuss more about this advanced bus clamping PWM technique, and we will justify the use of advanced bus clamping PWM technique. At this stage, I will not be in a position to justify the use of advanced bus clamping PWM technique because things are going against it. What is going against it? It produces higher Q-axis stator flux ripple than conventional switching sequence. But it gives other advantages, like it produces less torque pulsations in induction motor drives, which we are going to discuss hopefully in next lecture. And there I will tell you how this advanced bus clamping PWM switching sequences, or how advanced bus clamping PWM technique results in less pulsating torque in induction motors, and hence it is advantageous. Okay. And finally, a few equations. One of the equation is, for example, you can write the equation for harmonic distortion factor. Harmonic distortion factor based on stator flux ripple. Stator flux ripple. One of the equations is F square sector is equal to 3 by pi integration 0 to pi by 3 F square sub d alpha. F square sub d alpha, F square sub we have already found a few moments back in last lecture also. F square sub is equal to F square d sub plus F square q sub. Okay, that means the stator flux ripple in a subcycle is equal to the square of d axis component and q axis component, sum of these two squares, mean squares. And if you have to find RMS value of stator flux ripple RMS value, then it is under root of fd square sub plus fq square sub. Now if you integrate this f square sub, that is this mean square of stator flux ripple in a subcycle, from 0 to pi by 3, because our sector, for example, if this is active vector 1, this is active vector 2, the total angle is pi by 3. So I am integrating it 0 to pi by 3. That will give me mean of stator flux ripple in over a sector, because my sector is having total angle of pi by 3. So 3 by pi into integration 0 to pi by 3 f square sub d alpha. That will give me f square sector. Okay. And then the harmonic distortion, f distort, D-I-S-T, distort. That's distortion will be given by f sector. That's RMS value of flux ripple in a sector divided by V rep by omega. V rep by omega, where this V rep by omega is nothing but it is fundamental flux. This is stator flux ripple. If you divide it by fundamental flux, this will give you distortion, total distortion level in the flux. Right. With this, I will end my today's lecture. So today's lecture hopefully was although it was a bit lengthy, but I hope you'll understand why I could not break it into 2 lectures, because giving a break would break the rhythm and you may lose some very vital, important points. In today's lecture, we have discussed how actually we calculate the RMS stator flux ripple. Okay, once we have calculated its D components and its Q component, how we can calculate the RMS stator flux ripple. And we have also seen how the influence of various switching sequences on stator flux ripple. For example, influence of clamping sequences 0, 1, 2 and 7, 2, 1, influence of advanced bus clamping sequences or double switching clamping sequences 0, 1, 2, 1 and 7, 2, 1, 2 on stator flux ripple. And with some very good, very important points, we have found that if you use clamping sequence, for example, if you use clamping sequence 0, 1, 2 or you use bus clamping sequence 7, 2, 1, then if for alpha less than 30 degrees, the Q-axis stator flux ripple produced by clamping sequence 0, 1, 2 is less than the Q-axis stator flux ripple produced by clamping sequence 7, 2, 1 for alpha less than 30 degrees. But for alpha greater than 30 degrees, reverse is true. That is that Q-axis stator flux ripple produced by 7, 2, 1 clamping sequence is less than the Q-axis ripple produced by clamping sequence 0, 1, 2. With this background, we have tried to understand it with the help of flux. We have drawn that flux ripple diagram, those triangles, and with the help of those triangles, we have come to these conclusions. And applying this knowledge to space vector based 60-degree clamp PWM and space vector based 30-degree clamp PWM, we have seen that 60-degree clamp PWM gives highest THD among all the bus clamping techniques or among all the discontinuous PWM techniques, whereas 30-degree clamp PWM technique gives lowest THD among all the bus clamping PWM techniques. In a similar way, when we used double switching clamping sequences or advanced bus clamping sequences 0, 1, 2, 1 and 7, 2, 1, 2, there also we found that for alpha less than 30 degrees, after drawing those diagrams, stator flux ripple diagrams, triangles, we have come to the conclusion that the Q-axis ripple produced by double switching clamping sequence 0, 1, 2, 1 is less than the Q-axis ripple produced by double switching clamping sequence 7, 2, 1, 2 for alpha less than 30 degrees, whereas for alpha greater than 30 degrees, reverse is true. That is FQ 7, 2, 1, 2 is less than FQ 0, 1, 2, 1. Using this background, this knowledge, we have found that advanced bus clamping PWM technique 1 gives highest THD and advanced bus clamping PWM 2 gives lowest THD of the voltage and lowest THD of the current. Okay, and then finally we compared conventional switching sequence with clamping switching sequence. For example, we compared 0, 1, 2, 7 conventional switching sequence with bus clamping switching sequence 0, 1, 2, and we found that for this clamping sequence produces higher Q-axis ripple and hence higher THD in the current. But if we increase the switching frequency, if switching frequency is to be maintained same as in case of conventional space vector based PWM, you have to increase the carrier frequency by a factor of 1.5. That instead of increasing the THD or current ripple will reduce the current ripple, because some time back we have found that the stator flux ripple is directly proportional to TS. When you are increasing the carrier frequency, you are increasing the switching frequency, you are reducing TS, and hence you are reducing the stator flux ripple, and hence the stator flux ripple is less in bus clamping PWM technique than in conventional space vector based PWM technique using conventional switching sequence 0, 1, 2, 7 because of this factor. And we also compared advanced bus clamping PWM technique or switching sequence, double switching clamping sequence 0, 1, 2, 1 with conventional switching sequence 0, 1, 2, 7, and we found that 0, 1, 2, 1, that is advanced bus clamping switching sequence, produces larger or higher Q-axis stator flux ripple and hence larger distortion in the stator flux and stator current than conventional space vector based switching sequence 0, 1, 2, 7. However, we will be giving preference to advanced bus clamping switching sequences or advanced bus clamping techniques because they give us other advantages, like they result in reduction in the torque pulsations in the induction motor drives. We'll discuss that hopefully in next lecture. So with this, I will end my today's lecture. I advise all of you to go through this lecture and give me your feedback. I wish all the best to all of you. Thank you.